Yes, can you hear me?
Yes, we can hear you very well.
Okay, then I will share my slide. Can you see it?
Yep. Yes, we can. That looks good. Full screen.
Okay. So thank you for hearing my presentation. So my name is Legris Clement, and I am a first-year doctor student in the Research Center for Electron and Photon Science in Tokyo University in Japan. So I'm going to present the current status of the ULQ2 experiment and the required correction for it. So in this talk, I will present the proton radius puzzle that you know and how to determine the proton charge radius using electron scattering. And then I will talk about the current status of the ULQ2 experiment, as well as the required corrections for the ULQ2 experiment. So first, the proton charge radius puzzle. So as you know, before 2010, all measurement of the proton charge radius using electron proton scattering and atomic hydrogen spectroscopy found a proton charge radius of about 0.88 femtometer. But in 2010, using muonic hydrogen spectroscopy, the proton charge radius has been measured around 0.84 femtometer. And since then, using these three techniques, the proton charge radius has been measured either around 0.84 or 0.88 femtometer. So why is it so important to know the proton charge radius? So of course, it's one of the most primary characteristics of the nucleon. And so the proton charge radius is also greatly related to the Rydberg constant, which is essential for the spectroscopy. And as the energy of the s orbitals is related to the proton charge radius and the Rydberg constant. And so the cause of the discrepancy of the proton charge radius is not yet fully understood. So as you can see here, so as Jan explained before, so there's a discrepancy in the electric form factors obtained by the period experiment and by the mains experiment. And we can also think about the discrepancy in the proton charge radius obtained with the same transition using atomic hydrogen spectroscopy. So how do we determine the proton charge radius using electron scattering? So in the electron-proton scattering interaction, so we can define the momentum transfer, Q square, that depends on the energy of the incident and scattered electron, as well as the scattering angle. Then we can relate the cross-section of the interaction to the square of the electric and magnetic form factors. And if we express the electric form factor at extremely low Q square, so we can see here this term appear, which is the square of the proton charge radius as defined by Miller. So we get the proton charge radius by measuring the slope of the electric form factor at low Q square. But when we do the measurement, we actually measure the cross section. So we have a mixture of the electric and magnetic form factors. So in the ULQ2 experiment, we'll be carrying out the Rosenblatt separation to determine separately the electric and magnetic form factors. So we express the reduced cross section using the mode cross section and the tau and the beam energy. And so what we do is that we measure the cross section, so with a constant Q square, but with different scattering angles. So this will allow us to get separately the electric form factor and the magnetic form factors. So what are the specifications of the ULQ2 experiment? So ULQ2 for ultra low Q square. So we'll be measuring the electric and magnetic form factors for extremely small values of Q square between 3 × 10⁻⁴ to 8 × 10⁻³ GeV over C square. So this recently, it is one of the most lowest Q squares that have been achieved. So only recently the period experiment could go to 2 × 10⁻⁴ GeV over C square. So if you compare with mains data, for example, so they went down to 4 × 10⁻³ GeV over C square, so we'll be in a much lower Q square range. And to do this, we'll be using the lowest beam energy for electron scattering in the world, with a beam energy between 10 to 60 MeV. So we'll be carrying out the Rosenblatt separation with an angle between 30 to 150 degrees. And as we'll be using a CH2 target, we'll be able to measure the absolute cross-section measurement with 10 to -3 accuracy. So that's the goal. So how do we measure the absolute cross-section? So in the ULQ2 experiment, so we'll be measuring the electron proton and electron carbon scattering simultaneously, as we'll be using a CH2 target. And as you know, the momentum of a scattered electron on an X nucleus depends on the mass of the nucleus. So usually, if you are talking about with heavy nuclei, so it has a small effect. But in the case of carbon and hydrogen, so the mass of carbon is 12 times larger than the mass of carbon. So we have a large difference in the scattered momentum of the scattered electron. For example, in a classical case, so at 50 MeV and 90 degrees, we have a difference of about 2 MeV. And we can clearly see the difference in the peaks in experiment. So as you can see here, so we have a large scattering peaks for carbon, and we have a smaller scattering peak for proton. So when we measure the absolute cross-section, we can express the absolute cross-section of the cross-section of electron-proton scattering as a function of the cross-section of electron-carbon scattering. And what we need to know is the ratio of the event number and the ratio of proton and carbon nuclei in the target. So this means that we don't need to know very precisely the beam dose and the detector solid angle during this experiment. And so the goal of this experiment is to measure the proton charge radius with 1% accuracy. So we found that we need to have a precision on the electric form factor that is lower than 5 times 10 to -4 to achieve it with at least 9 Q² data points. So this will be pretty hard. And so this with the assumption that we will be able to obtain the cross-section with 10 to -3 accuracy, which is already a challenge. And so to do this, as you can see here, so to obtain 1 Q² data points, we'll need to have between 3 and 16 Rosenblatt data points. So for example, at low Q², like between 3 times 10 to -4 to, for example, to here, like 3 times 10 to -3 GeV over C². So we'll need to have between 3 to 5 Rosenblatt data points to obtain the electric and magnetic form factor at this Q². But when we will be measuring it at higher Q², so for example at 8 times 10 to -3 GeV over C², we'll need about 16 Rosenblatt data points. So it will take more time. So after taking all this into account and taking into account that one measurement is about 12 hours, so we found that we need a total beam time of about 1 month. So let me talk about the current status of the ULQ2 experiment. So first, here is Japan. You may have been there. So we are living in Sendai, about 300 kilometers north from Tokyo, and we are studying in the Research Center for Electron Photon Science here. And you can see a picture here. So one of the beamline of the Research Center for Electron Photon Science is used by the ULQ2 experiment. So it can produce a beam between 10 to 60 MeV with an energy spread of about 0.06% and a position spread of about 0.6 millimeter. And it can produce a beam intensity of about 1 microradian. So it's not a continuous beam, but a pulse beam. So it produces pulse with a duration of about 3 microseconds and with a frequency between 1 to 300 Hertz. So you can see a model of the beamline. So electrons are bended by bending magnet and go through the targets. So while most of the electrons go through a beam dump, some electrons enter the spectrometers and are focused by the magnetic field and reach the detectors placed in the focal plane of the spectrometer. So here is an actual picture taken last year of the ULQ2 experiment. So to be able to achieve our goal, especially with the Rosenblatt separation, we needed a special target chamber. So here you can see that we have a CH2 target, so electron beam is coming, and we have spectrometers and can go to from 30 to 150 degrees. So we designed this target, which is maybe the first variable angle target chamber in the world, and it allows to change the angle of the scattering angle by sliding this part and rotating the ball. So we can do this operation, so changing the scattering angle without breaking the vacuum inside the beamline and the spectrometers. So this allows us to carry out the Rosenblatt separation during the ULQ2 experiment. So let me talk about the spectrometers. So in this experiment, we use 2 spectrometers. The first spectrometer will be used for data taking, while the second spectrometer will be used as a luminosity monitor to see the state of the CH2 target. So it's about 1 meter long and 1 meter high, it weighs about 4 tons, and has a curvature radius of about 0.5 meter. It has an angular acceptance of about 10 millisteradian and angular acceptance of about 10%. So most of the current spectrometer place several detectors on top of the spectrometer to track the path of the particle. But in the case of the ULQ2 experiment, as we are using very low energy electrons, we cannot do this. So because we face a very strong multiple scattering, as the scattering angle is proportional to the inverse of the momentum. And so for us, it's impossible. So what we do is a single measurement of the electron position in the focal plane. And to reduce the possible scattering on the way, so we connect the spectrometer we keep it under vacuum and connect it to the target chamber. So the electrons are focused in the focal plane depending on their momentum and the horizontal scattering angle. So we can determine it from the X and Y position on the focal plane. And to be able to resolve the electron proton and electron carbon scattering peaks for any Q square, and especially the smallest Q square, we need to have a momentum resolution that is smaller than 10 to minus 3. So the detection system of the ULQ2 experiment is called SSD, so single-sided silicon strip detectors, developed by the JPAC Muon G-2 EDM collaboration. And it is and for each spectrometer, we use 2 detectors, each made of 2 times 512 channels, and located in the focal plane of the spectrometer. So the lowest one gives the X position to get the momentum, while the highest one gives you the Y position to get the scattering angle. So with a channel width of about 0.19 millimeter and a thickness of about 0.3 millimeter. And this is one kind of result that we obtained during an experiment. So you can clearly see the carbon scattering peak and the proton scattering peaks. And if you reconstruct, you project along an axis, you obtain this kind of result. So we had to obtain the relationship between the XY position and the momentum and the scattering angle, with the relation between this value delta and X is called the momentum dispersion, and the relation between the Y position and the angle is called the angular dispersion. And this delta here depends on the momentum of the scattered electron and the spectrometer central momentum. So it depends on the magnetic field of the spectrometer. So to obtain this, we used several collimators in front of the spectrometer. Especially one of these is called the sieve slit, with here you have the 5x5 Steve slit, and you can reduce the angular acceptance to 5 different points, theta angular points. So with so depending on the magnetic field, so you have different position. So for example, if you use a large magnetic field, you have a small delta, so a small X position, but with a delta about minus 0.05. But if you increase the moment, if you decrease the magnetic field, so you increase the delta in the X position. So if you compile all data that we obtained with 9 different magnetic field energy, with 9 different magnetic field, so you can get the angular and momentum dispersion. So for example, we found the momentum dispersion with about 10 to -3 accuracy, and we saw that the second order term was really small and has a very small impact. But in the other end, the angular dispersion, which is about 1 millimeter per milliradian, has a way larger effect, and the second order term is way larger with an effect up to 10%, and you can see it here. And most importantly, so we found that the momentum resolution was about 5 times 10 to -4, so it completely fulfills the requirement. So using the previous slide, I showed you how to obtain the delta, but we did not obtain the momentum of the scattered electron. And from the beam team, so we can derive the current, we can derive the beam energy from the current of the upstream magnet, but this is not precise enough, as we have a precision of the order of 1%, which is clearly not enough. So what we do is that we use the position of the carbon and hydrogen peak with this relation. So the X position is related to the momentum of the scattered electron. So if we express the ratio of the momentum of an electron scattered on a carbon nucleus and the momentum of an electron scattered on a hydrogen nucleus, we can write it as a function of the peak positions and the momentum dispersion. But we can also express this ratio as a function of the beam energy and the scattering angle. So we can, in the ULQ2 experiment, we'll be determining the beam energy directly from the experimental data, and this will allow us a precise determination of the Q square. So another task that has been occupying us for the last 2 years is the noise reduction. So we started this experiment less than 2 years ago. So 2 years ago, we faced serious background problem. So as you can see here, so we had this very strong background, so we could see the electron-carbon scattering peak, but we could barely see the electron-hydrogen peak due to the background. But we designed several LED shields that we placed around detectors, and we placed also several LED protection in front of the background noise sources, and we could significantly reduce the background noise. So here we can see the electron-carbon scattering peak and the electron-hydrogen scattering peak, as well as the electron-carbon radiation tail. But we still have a remaining background noise. For example, here also it's a bit too important. And so we have new noise reduction measure ongoing. So for the following experimental task, so we want to increase the precision on the momentum dispersion to be able to increase the energy and Q square precision for the determination of the proton charge radius and reduce the remaining background noise. And we still need to do determine the position efficiency and to see the position dependence. So we'll start the physics runs at the end of this year. So let me talk about the corrections for the ULQ2 experiment. So in this experiment, so we want to measure the cross-section of the leading order of the electron-proton and electron-carbon scattering with an accuracy of 10 to -3. But we actually measure many other Feynman diagram. So there's Bremsstrahlung, vertex correction, two-photon exchange, and vacuum polarization, and of course higher order terms. And we need to fit the radiative tail of carbon. But in the case of our experiment, we also need to fit the radiation tail of the electron carbon scattering. And as you can see, so this tail is really large compared to electron hydrogen scattering. So the yield of the hydrogen peak really depends on the parameterization of the carbon radiative tail, and we need to fit it really precisely. But for now, so as we've been concentrating on the noise reduction, so we have an outdated parameterization for the radiation tail, as we are using the convolution of three functions proposed by Professor Friedrich. So we use a convolution of three functions representing the internal radiative corrections, the external radiative correction, and the energy loss in the target. So of course, this parameterization is insufficient given the precision that we want to reach. So we are welcoming any contribution if you wish to help the ULQ2 experiment. So another correction I would like to talk about is the Coulomb distortion. So if we can use we suppose that the electron is an electron in a plane wave, incident plane wave, but it is actually distorted near the nucleus. So in our case, we cannot use the first order Born approximation. We need to go to the second order. So in here we are studying the elastic scattering. So the angular momentum of the proton does not change, and it is 1/2. So in our case, we face Coulomb and magnetic scattering. But actually, these scattering are really different as the Coulomb scattering does not change the electron spin orientation, while the magnetic scattering changes the electron wave spin orientation. So the classical treatment of the Coulomb distortion is the Feshbach correction. So we basically take the cross-section that is obtained with the first order Born approximation, and we multiply it by a factor called the Feshbach correction that only depends on the scattering angle. But this is assuming that we have the same correction for the Coulomb and magnetic scattering. Professor Tamae found that we need different correction for the electric and magnetic form factors, given that there is a change in the spin of the electron during magnetic scattering. So he found that we can use the Feshbach correction for the electric form factor, but we actually need to use Tamae correction for the magnetic form factor. So the Tamae correction also depends on theta, like the Feshbach correction, but you see that the term is quite different. So in his paper, he calculated the ratio of the form factors where Feshbach and Tamae corrections are used, and when only the Feshbach correction is applied. So you can see here that the magnetic form factor is reduced by a factor of about 1% when we take into account the Tamae correction. So it could be interesting to recalculate, to redo the Rosenblatt separation of main zeta using this correction, as it has an impact on the magnetic form factor, and it may change the proton magnetic radius. So you can see that in his era, it has an impact on about 1% on the magnetic radius. But if we go at lower Q square. So it starts to have a larger impact on the magnetic form factor. And in our case, in the case of the ULQ2 experiment, for the lowest value of Q square, the electric form factors is also affected by this correction. So this means that for the determination of the electric and magnetic form factor at ultra low Q square, we need to use the Tamai correction. And so, of course, this correction could be interesting to be used with mains data, but it is not interesting for the period experiment, as the angle is very, very small. Finally, I would like to have a word on the electron mass. So in most experiments, so the electron mass is neglected as for example, in the main experiment, the beam energy was always around higher than 180 MeV, and in the period experiments about 1 GeV. But in the case of the ULQ2 experiment, so we are using beam energy down to 10 MeV. So we cannot use this approximation anymore, and we have to use another expression which take into account the electron mass. So of course we must include the second order Born corrections, Feshbach and Tamai. And so I calculated the impact of this correction on the Q square and the cross section. So on Q square, you can see that between 20 to 60 MeV. So the Q square is not really changed. It has an impact less than 0.1%, but at 10 MeV, so it has about an impact of about 0.3%. So it's clearly, we cannot neglect it. And most importantly, if we look at the impact of the ultra-relativistic approximation on the cross section, we can see that it has not a strong impact for larger energy between 40 to 60 MeV, but between 10 to 30 MeV, it has a strong impact at large angle between 10 to 30 MeV, and especially at 150 degrees. So the error amounts to 4%, which cannot be accepted for the ULQ2 experiment. So if I summarize the corrections compared to previous experiment, so we'll take into account the radiative corrections, which will amount to a few percent correction, and we'll have to take into account the electron mass, which can amount up to 4%. And finally, the Tamai correction will have an impact on the electric form factor of 1% on the magnetic form factor, and also on the electric form factor at low Q square. So actually, we are starting the first measurement of the proton form factors tomorrow. So we are doing a test to try to observe the effect of this correction and how to analyze it. And I would like to thank you for your attention.